All right, so let's take a look at the polynomials review. This is meant to help guide you on your studying and make sure that you can check your answers and make sure you were on the right track with these concepts. So if I look at part 1 here, identifying the degree, leading coefficient, and constant. Well, let's start off with thinking about what makes a monomial, binomial, or trinomial. So in the first one, A, two terms being added together, this is a binomial. In our part B, we have three terms all unique being added or subtracted. This is a trinomial. In example C, I have one term, nothing being added or subtracted, just everything in one term. This is a monomial. And then finally, this one's meant to throw you off. 3x minus 7x plus 2x. You would think, oh, well, it's a trinomial because there's three terms. But what can we do here? We can take 3xy minus 7xy, make this equal to negative 4xy and plus 2x. Now, it's a two-term polynomial. Two-term polynomials are binomials. So ensure that all common terms are added together before you continue. All right, identify the degree of the following polynomials. Well, to get the degree of any polynomial, we have to look at the individual pieces of the polynomial or the individual monomials that make the polynomial and look at each of the totals of their exponents. So if I look at A, for example, I have 2x1, y squared, x3. If I add together the powers here, I have 1 plus 2 plus 3. That's equal to a degree 6 polynomial. Because the total of the exponents is 6. Now, if I go to B here, w, x, y, z, if I add all the exponents together, that's 1, 2, 3, 4, degree 4. W4, that's a degree 4. Therefore, this is a degree 4 polynomial. The highest degree is 4, and it's shared between both terms here. All right, I go down to example C here. I add their exponents. If I have 2 plus 3, that's equal to 5. I have AB, which is 1 plus 1, which is 2. And finally, I have a degree 6. Okay, well, which is the one that determines what the degree of the polynomial is? It's the highest degree available. So this is a degree 6 polynomial. All right, and then we go over to D here. This is 3kmn, which is 1, 2, 3, degree 3. Then we go k2 plus m1, which is 3. And then finally, k and n3, that's a total of 4. So the degree of this polynomial is the highest degree available, or degree 4. Okay, now I could expand upon this by asking for the leading coefficient. Let's do that in our next problem here. All right, and then we go into example 3, which says, let's identify the leading coefficient and the constant term if possible. So the leading coefficient comes from the one with the highest degree. So if I add these together, 2 plus 3 is 5. B, 1 plus C2 is 3. And then finally, we would have a 0 here because we know we could actually write this as B to the 0 or even C to the 0. And anything to the power of 0 is 1. So that would be the term left here. Now, what is my leading coefficient? I immediately look to the one that determined the degree of this polynomial, which is our first term here. I look at the coefficient of that and say, oh, the coefficient or leading coefficient is equal to 4. Okay, now what is the constant term? The constant term is always the one that has no x, y, or any variables on it. So what is the term with no variables? It is the negative 2 on the very end here. So I take this and I go, my constant term is equal to negative 2. How do we know? Because it has no variables, or it remains constant no matter what values we choose for B and C. All right, I go over to example B here. 8 CE. This is 1, 2, 3, sum of a total of 3 there. We have C3 D1 and 2. This is a total of 6. And then finally in the last term, we have 2 plus 2 plus 3, that's equal to 7. So this is a degree 7 polynomial. What is the leading coefficient? It comes from the one with the highest degree. It is 18. So my leading coefficient is equal to 18. Now, is there any term with no D, C, or E? No. In this case, it is all terms with variables, so we have no constant term or nothing that is unaffected by the different values of C, D, and E. So I can just write below no constant. All right, now part 2, algebra tiles. If we want to construct a polynomial given algebra tiles, well, let's remember here, we have strict notation of positive tiles are shaded, negative tiles are unshaded. So if we go one by one on these, for A, it doesn't look like we have any negative or unshaded tiles. And now we should be very clear that our shaded tiles that look like a complete square or a box, these are going to be our x squareds. Our x's are these skinny rectangles, and finally we have 1 for our individual blocks here. The polynomial that describes this, I have 5 of the x squareds. I have 6 of the x's, and finally I have 3 of the individual ones. If I go over to B, I have a couple unshaded tiles for both, and then a couple shaded. Well, I have a total of negative 3 x squareds. I have 1 x squared, so that's positive. I have negative 4x. I have plus 3x. I have negative 1, and then finally plus 6 of the individual tiles. Now, this is where it becomes really important of your organization. You could either highlight them to differentiate them. You could underline them. I'm going to underline them. If I have squared terms here, well, I'm going to single underline them. If I have x terms, I'm going to double underline them. And finally, with the constants, maybe I do a squiggle in order to identify these. Negative 3x squared plus x squared is negative 2x squared. Negative 4x plus an x is equal to negative x, or negative 1x. And then negative 1 plus 6, this is equal to plus 5. There is our polynomial. Now, I go down to example C. I have positive 2x squareds, which are here. I have negative 3x squareds, which represent the unshaded part. I have negative 4x, or negative 4 of the unshaded rectangles in this case, so the longer skinny rectangles, plus 2x. I have plus 3, which represents the shaded 1 tiles, and then finally minus 5 for the unshaded 1 tiles. Now, yet again, I want to organize these in a differentiating manner. I'm going to maybe underline again with my x squared terms, double underline my x's, and then finally squiggles for the constant. If I add my x squared terms, it's 2x squared minus 3x squared. This is going to be equal to negative x squared. Negative 4x plus 2x, this is negative 2x. And finally 3 minus 5, this is going to be negative 2 here. So my polynomial combines to the following. All right, let's flip over the page here. Simplifying the following expressions. Well, to simplify an expression means to combine all the like terms. So if I look at my first term here, what you could do is you could actually rewrite this with 3y plus 4z plus 6 plus 2y minus z minus 4. Reason I can just drop the brackets is because no signs change, and now I just want to collect the like terms. I have a total of 3y plus 2y is going to be equal to 5y. 4z plus a negative z, this gives me plus 3z. And then finally 6 minus 4 for the constant terms, this is plus 2. All right, I go over to B here. To collect the like terms, it looks like they just want me to identify the common terms. My x's or my x squareds are going to get the single underline. My xy's will get the double underline. And then finally my y terms, I may just use a squiggle to represent those. When I combine the like terms, x squared minus 3x squared is negative 2x squared. Negative 2xy minus 6xy is negative 8xy. Negative y squared plus 2y squared is positive 1y squared. Now, if you write in the 1 here, that is totally fine. There's nothing saying you can't do that. A lot of the times the answers won't be written with that 1, but if you write this 1 in, it is still correct here. All right, example C here. We know as soon as we see the negative here, it will flip the signs in the bracket to its right. Why is that? Well, we know the coefficient is actually negative 1, and if I take a negative 1 and expand it in the brackets, this becomes 2c minus 3 minus 1c. Negative 1 times a negative 3 is positive 3. And so if I combine the like terms here, 2c minus 1c is equal to 1c. Negative 3 plus 3, those two eliminate. They're the same term, opposite signs. And so our answer is 1c, or simply c. Okay, now if I go down to number 6 here, expand and simplify. Now I just have a term where I have to expand or take away all the brackets and then put the like terms together. So by order of operations, I know that I'm going to have to look at brackets, exponents, then multiply, and then deal with addition and subtraction after. So for my example A, I leave the 3x, I expand the 2 into the brackets, and this becomes plus 10x. 2 times negative 3 is negative 6. And now I combine the x terms together. 13x minus 6. There we go. Simplified, expanded, and simplified. If I go over to B, I have that same type of technique that's going on here. I have to multiply the coefficient into the brackets on both of these. This is going to be equal to 12u. Negative 1 times 4 is negative 4. 2 times 3 is positive 6. 2 times a negative 2u is negative 4u. And now I combine the like terms. 12u minus 4u is 8u. Negative 4 plus 6 is positive 2. All right. And then finally, I have an example where I have a binomial times binomial and then some coefficient times the binomial. In the first, I'm going to FOIL this out to expand it. So it's equal to x times x, which is x squared. X times negative 1, which is negative 1x. I then go 1 times x and 1 times negative 1. This is plus 1x minus 1. And then we take the negative 3 and we expand it into the brackets. Anytime we have this negative and it's being put into the brackets, we know the signs will flip. It's going to become negative 3x. Negative 3 times a positive 2 is negative 6. Both of the positive terms in the bracket went negative. And now I combine the like terms. I only have 1x squared. If I take a plus minus of the same x, well, those eliminate. And so I have negative 3x. And negative 1 minus 6 is negative 7. Now, here's the pattern I want you to realize from when we expand and simplify. You only have one x term, one constant term, one u term, one constant term, 1x squared, 1x, one constant term. At the end, when you expand and simplify, you should have one of each of the powers of your different polynomials. So if you only have u's in the end, well, you should only have one u and then one constant. Similarly, if you're dealing with something with a degree 2, well, you should only have something with one term with degree 2, one term with an x or a degree 1, and one constant term. All right, expanding binomials in the form of a plus b squared or a minus b squared, it's critical that we do not apply the power rule, meaning to expand these polynomials or to expand this binomial that's squared, I need to write it as the following. The same binomial written out twice. It would be completely wrong. This is completely wrong, and I'm going to do it in red just to indicate it's completely wrong. It is completely wrong, and I'm even going to put x's along the way through this line, and maybe even clearly right over top. Do not do the following. If you write a plus b squared as a squared plus b squared, or if you write a minus b squared as a squared minus b squared, that is completely wrong. We do not apply power rule. To expand these, here's how we do it. If I take the example below, this is equal to x plus 4 times x plus 4. Now I FOIL this. X times x, x times 4. My first two terms are equal to x squared plus 4x. I then go to my next two, 4 times x, 4 times 4, this is plus 4x plus 16. Now, this is equal to x squared plus 8x plus 16. And that is my trinomial when I expand this binomial squared. And what we actually found out is we had a whole lesson on these types of problems where we called this a perfect square trinomial. It's something with the same factor, meaning it can be one binomial squared. Now I'm going to go over to b minus 2 squared. I'm going to rewrite this as b minus 2 times b minus 2. If I FOIL this, it's b times negative 2. That's equal to b squared minus 2b. Now I multiply negative 2b, and negative times negative 2, this is negative 2b. Negative 2 times negative 2 is positive 4. I collect the like terms in the middle, and this becomes b squared minus 4b plus 4. Now the connection we made in class to these is that if it's a perfect square trinomial, well, from the trinomial back to the factors, I should recognize that the middle term is negative if the original term was negative in the binomial. If it was positive, it should be positive in the middle when you go into your trinomial, when you expand it. So that pattern should clearly exist. If you're getting a positive when the binomial was negative to start in these cases, something went wrong. So double check your signs there. All right, last piece, part 4 is to factor. Factoring includes multiple things. We can go by grouping, inspection, difference of squares, or the perfect square trinomial. Step 1 of factoring always is to remember to take out the GCF or the common factor. It always is the case. Please, every single problem you do, make sure to pull out the greatest common factor. So let's look at some factoring examples. 14a plus 21b, what's the common thing I can remove? Well, if you correctly identify that they both share a factor of 7, this is perfect. So my factor term is 7. And if I divide 14a by 7, I'm left with 2a plus 21 divided by 7 is 3. And we throw the b there. Our greatest common factor gets placed on the outside of our factor here. Or it gets removed out front because we're dividing all terms by that number. Now let's do the same thing with part B here. I divide both terms. What do they both share in common? Well, I can divide both by a negative 5, and I can divide them both by at least 1x. So this is going to be equal to negative 5x. The GCF goes out front, and now negative 5 over negative 5 is positive 1. X squared over x1 by quotient rule is equal to x. Negative 10 over negative 5 is positive 2. And x over x here, it simplifies down to x to the 0, which is x. X0 is always anything to the 0 is just 1. So we close our brackets and we're done. And yet again, my GCF or whatever was common gets moved out front. All right, let's try a harder example here. If I go into C here, I underline it, indicating that I'm going to divide all terms by this common GCF. 12, 16, and 32 all share a factor of 4. The least amount of shared m's in this case is 1. They all share at least one m, so I'm going to put m here. I then move on to the n's. The least amount of n's shared is 1n, or n to the 1th power. Now, I rewrite this as my GCF, or the 4mn out front, and I divide each term by that 4mn. 12 divided by 4 is 3. M squared over m leaves me with m1 by quotient rule. N squared over n gives me n by quotient rule. 16 over 4 is plus 4. M over n is m to the 0, or just 1. N3, or n cubed over n1, leaves me with n squared. Negative 32 over 4 is negative 8. M3 over m1 is m squared. And finally, n over n is just n0, or 1. So there's our GCF on the outside and our remaining factor on the inside, or remaining values on the inside brackets. All right, now if I move on to E here, E, remember, if we look at a greatest common factor, it doesn't always have to be just a monomial. In this case, what is the common binomial that both of these terms share? It is the s plus 5. Here's a parallel way to see it. I could write this as sy minus 2y. And most of you would tell me correctly that if I remove a y out front, this is the greatest common factor. What am I left with? S minus 2. So this is no different. Now we just have a binomial that is shared between the two. So that common binomial, or the thing I can remove out front, is s plus 5. What am I left with? I'm left with the two coefficient terms, or s minus 2 as my second factor here. If I go into my example f here, you need to be really careful. The coefficient of my second term here is 1. Please write that. If you see that there's nothing there, you have to write 1. Here's why. My greatest common factor, or the common factor, or the common binomial between these two, is our g plus 6. So I can rewrite this as g plus 6 being moved out front. What is left over? It's my coefficient terms of 1 and 2g being added together. 2g plus 1. All right, now I go down to example G. It can be done by factoring of inspection, or factoring by inspection. Why? Because the coefficient term here, or the coefficient of our degree 2, is 1, or a is equal to 1, more specific terminology there. So if a is equal to 1, we know we can do this by inspection. We must multiply to make the outside number 12. And we must add to make the middle number, or 8. The two numbers that can do this for me are 6 and 2, and therefore, because we know a equals 1, we can jump right into our factored form. It's y plus 6, y plus 2. We keep the signs of each of those numbers that make this true, and then we throw them into their factors. All right, let's look at h here. H is p squared minus 15p plus 26. We know the a value is equal to 1, and therefore we can do this by inspection. If I do this by inspection, what multiplies to make the outside number 26? And then what adds to make the middle number negative 15? So off to the side, you could do this here. What are some things that multiply to make 26? Well, we have 2 and 13. We have, in this case, 26 and maybe 1. But right away, I almost want to pause and say, okay, well, if 2 and 13 can sum to make 15, let's see if we can make this work. If I put negative 2 and negative 13, that definitely multiplies to make 26 and adds to make negative 15. But so does negative 26 and negative 1, except it doesn't add to make negative 15. So I'm going to use negative 2 and negative 13 and apply these right away as my two factors, p minus 2, p minus 13. Now, the nice thing about these is when you factor them, you should be able to reverse. We've done this before on the previous page. We expand a binomial to get a trinomial. If you want to double check your work, I would expand this binomial by binomial and see if you can get back to that original trinomial. All right, now this one heavily relies on our knowledge of what is step 1 of factoring. It's to always remove the GCF. So we need to remove the GCF. Okay, when we remove the GCF, this is equal to every term here shares a factor of 4. So I'm going to remove 4 out front, and if I take 4l squared and divide it by 4, I'm left with l squared. If I take negative 8l and I divide it by 4, this is negative 2l. 4 divided by 4 is plus 1. And now I look at this and I say, if the coefficient here is now a equals 1, or the coefficient of the degree 2 term is 1, I can factor this by inspection. So I can go down below and say, what multiplies to make the outside term, positive 1, and adds to make the middle term, negative 2? Well, the things that would do this for me are negative 1 and negative 1. And now, here's what I could do. I could just immediately go 4 L minus 1 times L minus 1, and then this would combine to make 4 L minus 1 squared, because we know if we have the same binomial, we can just write it as squared instead. We actually covered that one on the previous page. But what if I want to do factor by grouping? Well, if I want to do grouping instead, I'm going to do that method below here. So grouping. In order to do grouping, I have to go equal to 4 in the brackets L squared minus 1L plus 1. Close the bracket. I group my first two terms. I group my last two terms. And then from here, this is equal to 4. What is the common thing I can remove from both L squared and L? I can remove out L. So I'm going to bring L out front, leaving me with L minus 1. Of my second grouping, I can remove out this negative because I never want to have the negative there. Negative 1, that flips both the signs to L minus 1. And now my common binomial is the L minus 1. I move this out front to be 4, L minus 1. And my second factor is the two outside terms here, or L minus 1. So we can do factor by grouping, or specifically decomposition, which is the longer form of factoring, to show that this is actually true. Or as soon as you know that the a value is equal to 1, we can go right to the factors here. And then we can simplify it as the following. Okay, if I go down to example K here, example K, this is actually a special form of factoring that's being hidden by a GCF. Step 1, I'm going to remove the GCF. I can divide both of these by 3, leaving me with x squared. 27 divided by 3 is minus 9. And now I have two terms in the brackets being subtracted from each other. I should immediately have my red flags up and say, okay, something is going on here. It's a special form. If I take the square root of x squared, it's equal to x. If I take the square root of 9, this is equal to 3. They are both rational numbers when I square them, meaning this is most likely a difference of squares. This is equal to 3. And to make a difference of squares, it is going to be x plus 3 and x minus 3. It is the two things that were perfect squares subtracted or added from each other to make the two factors. Now, another way you could show this, if you wanted to, was to say this is equal to 3x squared plus 0x minus 9, and factor this like a regular trinomial. You know a would be equal to 1, and you need two things that multiply to make negative 9 and add to make 0. That's negative 3 and 3. And as soon as I have my two numbers like that, I can say this is equal to 3x minus 3, x plus 3. I can throw them into my two factors. So both methods work. However, you just have to have the insight to say, if there's nothing written in the middle, I have to write this just as a way to placehold that there's nothing there, so that when I do my factoring by inspection, I'm able to come up with a number that sums to something and adds to make something. All right, and then lastly, we have m squared plus 8m plus 16. I can do this by inspection because I realize the coefficient of my leading degree term is 1, or a equals 1. I have to multiply to make some number and add to make some number. I'm going to phrase it like this just to show a comparable alternative. I have to multiply to make my outside number 16 and add to make my middle number, which is 8. What will do this for me is 4 plus 4 and 4 times 4. So when I go to my factors, which I will draw a squiggle line down here to create more room here, we have m plus 4 and m plus 4. This can be equal to the same factor multiplied by itself is m plus 4 squared. Now, if I wanted to do this by grouping instead, here's the alternative. This is method 1. Method 2, method 1 being inspection, method 2 being factor by grouping, m squared plus 4m plus 4m plus 16. I can factor this by grouping. Take the first two, take the last two. the common term in the first one is m, leaving me with m plus 4. If I take a common term off my second grouping, they both share a factor of 4. This is plus 4, leaving me with m. 16 divided by 4 is plus 4. And now my common binomial is m plus 4. And what am I left behind with? The m and the plus 4, leaving me with m plus 4, which can also be m plus 4 squared. All right, good luck with the rest of your review.